as the cold beer that we have in the building. So if you are around, you still have time to leave your office and come over and listen to the colloquium, because we're gonna wait for 3-4 minutes for latecomers anyway. So you still have time. Yeah.
Yep.
Okay. Good. Yes. So I can. The camera here is interestingly blurry, but that's this camera,
Yeah.
I guess.
Camera in the back.
Yeah, it doesn't have a very good resolution for some reason. Good enough. So let me open. Ah, okay. If I open the voice here, we will have an echo.
I have to switch off the mic. Yeah.
Yeah, and I can do it like this, right?
Just hold it like this, then it's fine.
Okay. Yeah. All right. So I can shield it like this so that we don't get an echo. All right, maybe I can start with the introduction, and then yeah, I will do that. No problem. So welcome everyone. Today's talk will be given by Martijn van der Werf, and I'm happy to introduce him. He's an assistant professor in the Information and Computing Sciences department, and he has been working on modeling and analyzing behavioral aspects of software architectures for software products. And he has a dual PhD in computer science from Eindhoven University of Technology and Humboldt Universität zu Berlin. The floor is yours.
Thank you.
I will take the computer with.
Yep. Yeah, so what I would like to talk about is, well, latest work. And a paper that we just got accepted at the Petri conference, talking about data and process resonance. And I would like to give an example on why it is difficult to have both processes and data. Consider the following data model. We have courses, we have lecturers that are qualified for some courses, and we have course instances. And of course, a lecturer gives a course instance, and students then enroll for a course instance. And a course instance should be taught by exactly one lecturer. So this is the model. And it's a world where we have too few lecturers. So we also have a process model. So here's the process model in BPMN notation. And what do we see in the process model? Well, we see the education manager opens a course instance. Then students can enroll for the course. That can happen for many students. Then a tender is being opened for who would like to be lecturer, and then the lecturer is being selected. So we have a form. So the form that the education manager has to fill in is, well, select the course for which the course instance will be, select when it will start, and select when it will end. And then I try to submit this. Well, my data constraint says there should be a lecturer for a course instance. So my process hampers because of the data model. So my process wants to continue, wants to fill in data, but my data model says, well, there's a constraint that's not satisfied, so I can't continue. How do you find such problems? The problem of many data modeling languages is that they don't focus on the process. And the problem of process models is that they don't focus on the data aspect. And where does it go wrong? In the combination. So how can you think about the combination of the two? How can you start looking into what are elements of processes, what are elements of data, how are those combined? That's basically what I'm really interested in and what goes wrong often. So What I would like to do today is give a quick introduction about Petri nets with data, because I guess most of people in my audience don't know Petri nets as well as I do. And there are a few in the audience here. We have a property, so we want to add data to it and then start looking into what happens actually. We also have then a notion, and that's the notion that is new, that's called identifier soundness, because then we can say something about correctness. And I will give some interesting subclasses that show that these properties can be useful. So first, a small introduction to Petri nets. Petri nets are different than labeled transition systems or automata in that we have a distributed state. So instead of just having a global state from which you decide what are the actions, in Petri nets we do this locally. So that means we have places, these big circles, that indicates kind of a condition of a system. And then we have tokens, and those tokens represent elementary entities of interest. So for example, maybe this place A is a set of, it represents a doctor in the house. And then these two dots, these two tokens mean actually doctors. So that way, the tokens represent elementary entities. And then what is the marking or the state of the whole net? That is basically the configuration of tokens over the different places. So in this case here, in this model, we see 2 tokens in place A, 3 tokens in place B, 1 token in D, and 1 token in F. And then a transition is a state change. And that is a local change. So what does a transition do? It checks for all the places that it is connected to, is there a token in that place? And if in all input places there's a token, then the transition says, I'm satisfied, I'm enabled, I can fire, I can do a state change. And then the state change is going for the output places. And so you remove a token from the input places and you produce it in the output places. So it's a local state change. And so in this net, you see there are 2 tokens here in place A, 3 tokens in place B. So that means that transition T is enabled. All input places have at least 1 token. So transition T can then fire, that's the change of the state. And that firing, executing it, just means remove 1 token from each input place and produce it in one output place or in all output places. So in this case, the transition is enabled. It removes a token from A, it removes a token from B, and it produces tokens in D, E, and F, like this one. There it is. The animation is a bit slow. Yeah, so this is basically how we model state changes in Petri nets. And it's all local. That's the whole trick of Petri nets. Yep. All input places should have a token. Yes. No, it's enabled. It can fire. Yeah, it doesn't mean it fires. It can fire. And then you choose randomly which one will fire. Then the state changes, and you calculate again what are the transitions that are being enabled. There's one caveat. There's no law of token preservation. So that means if there are 2 being consumed, there can be 3 output, or there can be none being output, just depending on the transition. And so this is a mistake often made. People think in terms of tokens being preserved, but it's nothing more than just something that's being consumed and something that is produced. So there is no relation between the tokens that are being consumed and the tokens that are being produced. They're just entities and they're there. And so that is one of the basic things in Petri nets. And this one can fire, of course, again, giving a new marking. But now transition, now transition T is not enabled anymore because there's no token in place A. Why do we like, or why do I like Petri nets a bit more, is because it makes my models a bit smaller. So here we have a small Petri net, and we have some execution. So typically we express this in terms of automata. So the behavior of Petri nets is actually an automaton. So how does it work? So we look into the initial state. In this case, there's 1 token in place P1. So that's also what we model. It's really slow at the moment. See, it's so slow that That never happened to me before. Well, anyhow, I'll just continue with the story. This is really interesting. Wow. Fortunately, I was not too far in my story. So there we are. Let's see whether it now works. Yes. So we're in a state. P1 has one token. I don't denote a 1. It's just saying P1. Transition A is enabled, so it can fire. It results in P2, P3. And it's a new marking. And then transitions B and C are both enabled. So we labeled it typically with red arrows around it so that we know which ones are enabled. So P2 and P3 are enabled. Well, you can choose one of them to fire. So let's say transition B fires. You get a new state with P4, P3. Then transition C could fire. It gives us state P4, P5. Then transition D could fire. That gives us state P6, P5. Transition F is not yet enabled because a token in P7 is missing. If transition E fires, we have P6, P7. And well, then transition F is enabled, so it gives us state P8. And of course, this is not the whole model. If you really look carefully, then there were 2 transitions enabled in the beginning. So we could finalize the model. So we could have also chosen to have transition C to be fired, giving state P2, P5. And if I continue this whole model, then this Petri net has the behavior of this automaton over here. So basically, Petri nets allow you to model exponential big systems. And you can really show what happens with concurrent parts, and the concurrency is shown in the model, as it were, and not hidden in the transition system. So that is one of the advantages of why do we use Petri nets. It allows us to model concurrency and to think in terms of concurrency. So it's being used quite a lot, and one of the most frequent used models are workflow nets. And a workflow net is basically a description of how would something, a work process, how would it move? And then we have an initial place I that says, well, this is the start. And we have a final place F, that's the goal. And all transitions and all places should lead to that goal. And that's what we call a workflow net. So all nodes should be on a path from the initial state or the initial place to the final place. And then the property that we all love is when the workflow is sound. It should be correct. And what does it mean? It means 3 things. The first one is it's properly completing. So that means if I reach my goal, I am at my goal and there's no work left. The second property says weak termination. It's always possible to reach my goal. And the third property, quasi-liveness, says every transition has some function in the process. So it is always possible for each transition to start from the initial, to reach the transition and execute it. And so each transition makes sense in the model. So those are the 3 properties of soundness. And we always use those if we talk about business processes, BPMN models. We typically ask, are they sound? And what we do is under the hood, we translate those BPMN models to Petri nets, and then we check soundness. So soundness is being used quite a lot in business process management and modeling. The only problem is that it describes a single process in isolation. So I just describe a single process instance, how it goes. And so in the example I just gave for the course, it's for one course instance and how that course instance progresses over time. And if a new process instance arrives, I just have a completely new workflow net that starts again. And of course, that becomes funny because process instances or data is not just in isolation. We don't have a single case running, we have multiple cases running together. So how do you do this? So if you have multiple cases at the same time, how do you handle this? Well, a simple thing would be, I just add a transition on the beginning and a transition at the end. So basically, this just says, well, we create a new process instance. And here at the end, we say, well, if we reach the goal, we just remove it again. So that means that this initial token in place I can just remove. So now I modeled multiple cases at the same time. And why does this work? So this is always a trick question to students. Is this initial transition enabled? And the answer is yes, because all input places have a token. There are no. Yeah, so this initial transition is always enabled. That means that my reachability graph is infinite. Meaning the automaton is infinite. I can't model it on paper. It's too big. But here's the model. Yeah, so I can't analyze actually because my reachability graph is infinite. What do you do? Well, different techniques are being used, and that is what is called case soundness. And so instead of saying we just have one instance, we start with k instances, and then all k should move to the end. And so basically, case soundness up to case soundness. Case soundness means it is for exactly that number k working. Up to case soundness means it works for all of them up to k. And if it works for any number k, then we call it generalized sound. And so we can write this down as properties. There they are, but it's a bit tricky. So let me give an example. Here we have a workflow net. So this is a beautiful workflow net. We start with an initial token in the initial place. Decision A can fire, and I can just ask, is it one sound? There's one token here, is it one sound? And well, transition A can fire, it produces a token in place P. Transition B is enabled, can fire. And now transition C is enabled, but transition D is not enabled because there's no token in place E. Yeah, so the only thing that can happen is transition C to fire. So it is not one sound. I will remain in this loop forever. Now, next question then, is it two sound? And so we start with two tokens. Decision A can fire, gives me a token in place P. Decision B can fire, C can fire. And so there's the token, E can fire now. Now let's fire A again. Transition B fires, and suddenly transition D is enabled. So we fire transition D. There it is. Transition E is now enabled, and there are two tokens in the final place. So that means that this model is two sound. So it's not one sound, but it is two sounds. And this often happens with arbitrary numbers. So you really have to be very careful with my model and what happens. So generalized soundness is somehow a very difficult notion to grasp because you have to think concurrently in all process instances at the same time. That makes it difficult. So you could do this. Generalized soundness is decidable, but actually there's a different problem to it for me as well. So let me explain what happens. So we start a new process instance. So the first one fires, and I'm still for my first case. So transition A now fires, and well, and we can choose which of the two shall we fire. So we fired transition A, and we fired transition B for the first instance. So transition C is still enabled for that first instance. Now I start my second one. So my second instance, I fire transition A. I fire transition C of the second instance. And now suddenly transition D is enabled. But actually it is of process instance number 1 and of process instance number 2. But generalized soundness just removes all this information just as there's a black token. I don't care what instance it is, there is a token. Yeah, so the problem of up to case soundness and generalized soundness is that it mingles all those instances. So you don't know anymore what was of which instance. So how to solve this? And the way to solve this in Petri nets is to add colors. And so basically what we say is, well, I call it an identifier, but it's basically a color. So instead of just saying it's a black token, I just give it a color. So that means transition fires, it generates a red instance, and then I can fire transition A. And there's this red instance, transition B can fire. So there's the R, so that is still that first instance AB. And then I can fire for the second instance. So I create another one, let's say yellow. And so I fire the yellow one, transition A fires. So on P and Q, there's now also a yellow one. And now let's fire C for the yellow one. And there it is. Transition D is not enabled because there's one red and one orange or yellow. And we just say, well, transition is only enabled if the colors are the same, the identifiers are the same. So this solves the whole problem of mingling all those cases. Problem solved, you would say. Well, the problem is this is as expressive as classical workflow nets. So why would you add colors if it's as expressive? What does it add? If it doesn't add any expressivity, why would you like it? So we need to look a bit further. And think of those tokens as a process instance, the entity in the database. You could also talk then about resources. So, for example, I could say, well, transitions B and C are in some kind of critical section. There's some mutual exclusion going on. And so, for example, there's a resource needed in order to do B and C. And so that means that transition A requires a resource, takes that resource, does B and C, and then with transition D, it returns the resource. And so this way, I model the critical section with transitions B and C. And so this is the typical trick in Petri nets to model critical sections and resources. However, there's of course this token over here. And it's a resource, so it's again a different color. So let's just take a black one. Now, transition A fires, we have this red one. And we fire it again, and then we have the yellow one. But transition A is of course not enabled because it needs tokens of the same identifier. And we have here a red and a yellow one, and here we have a black one. And this one just keeps on generating new colors. This one remains black, so that means transition A is never enabled. Yeah? So we have this transition A, and it's just waiting constantly because it can't match all those. So what did we do? We cannot model global resources, so our solution was we add two types of places. We have places where we put those identifiers, and we have global places that are those resources. And so then basically we say this is a resource called agent. And if you start doing this, then suddenly we have multiple types of identifiers. We have the agent resource and we have our case resources. So that means I can just say, well, this place is actually, the resource place is actually of type agent. And the token in there is of type A1. It's identifier A1. You can just start naming it. And all the other places we have, so I, P, Q, R, and S, and F, they are for the case. So I can annotate them with the case. So I and F are just the case, because that's to identify the type being created.
I could have used a single case the identifier.
Yes, but then it's not a global resource anymore, and no mutual exclusion.
But it's going to grow a little.
Yes. Yeah. Yeah. Because then basically you have to do this for any identifier. And in Petri nets, we don't want to extend the net. We only want to extend the tokens in the net. The net should be fixed. And so the places and transitions are fixed all over the course of the run. But what we would like is then say, well, this transition A takes a case token, takes an agent token, takes it with him with B and C, and then with D, it releases the agent again. And so we annotate those places by saying, well, this place actually carries a case and an agent. And for all four places here, we just say they carry a case and an agent. Yeah, that way we can model again. And so now it works again if I just say, well, I add the variables. And so there they are, and now we have a full net. So I just take the identifier of the one, of the other, I combine them in a combined token containing both of them, and with D I release them. So the C continues for the case, and the A goes back here to the resource. Yeah, so this way we can start modeling again, and we have all these identifiers, and it all looks beautiful. But then you get a model like this. This is a web shop. So what do we have in this web shop? I'll just walk you through. It's a slightly bigger model. There are three parts in it. There are three colors, because adding all those identifiers becomes a bit clumsy in the model. So I just use a coloring scheme. That's where the name colored Petri nets come from. We color the places. So we have a part for products. So transition A means I can create a product. Transition B means I delete the product. And products have two states. Either they are available or they are unavailable. And with transition C, I make them unavailable. With transition D, I make them available again. So that's this loop here. And I can add the products to what I call the offer. So basically, this whole process says, well, it's all about creating an offer. I can add some products to the offer. I can accept the offer, deliver it. It should be paid. So we send an invoice. We might send some reminders for that offer. We pay the invoice, and we finish the offer. And of course, we have customers. So we need to create customers for which the order is being created, and we delete the customer. And we can delete the customer. And if a customer does not pay, so basically we send an invoice, you send some reminders, and the customer does still not pay, then we can block it. So this transition M says, well, I block a customer, meaning the customer is being from here the available customer, it goes to the blocked customer. Yep. Send invoice, because we just need the offer for that. It might be that I need you're right, I could add that it's a read-write for the customer. I just left it out. I assume that that information is in the offer. That's a modeling choice. And now my question to you, is this model correct? Huh? Because that's what we want. We want to have correct models. And if I look to this model, then I'm like, I don't know. I hope so indeed. And that's why we model them. Yeah. So, but it is a question. How do you solve this? How do you look into this? And the problem is, if we add these colors, we start to have problems with analyzability of Petri nets. Because adding a color means becoming undecidable in your reachability problem.
Descriptions of transitions. I have a color. I can generate
Yeah, but the problem is there are infinitely sequences in this model.
So I just need to, if it is correct, then I will reach the end in a finite amount of time.
Nope. I can give you models where this doesn't work. The problem is in the intermingling and knowing the distribution of the states. You need to take the state into account in order to analyze the model. So I want to analyze those models and saying, yes, it is correct, or saying, no, there's a mistake in it. How do you do this? Well, that brings me to the next part, identifier soundness. So we found something that we can say, well, whether it is correct or not. There's only one pitfall. Property itself is undecidable. I already say it now. Yeah, but what is actually the property and what happens? So what is the rationale behind it? So again, going to this net, then I can identify some special transitions in this model. The first one are what we call emitters. Those create new identifiers. And if I look to this model, then transition A creates products. Transition T creates customers. And transition G creates offers. This transition G is, by the way, the one that makes the model infinite. You directly see this one makes it infinite if you wouldn't have seen it from transitions A and T. So those create new identifiers. I can also find some other transitions, namely the collectors, that remove identifiers from the net. For example, here transition B, it removes a product. So there's one. Delete customer of the collector. And here finish offer is a collector for the offer. Yeah.
So what does it mean to have a correct model?
So that's what I'm trying to arrive at. So what would be a good solution? Well, soundness says everything should go from the initial to the final. If I would translate this to identifiers, then you say, well, it should go correctly, so it should be emitted. And once it's being collected, it should be removed from the net. That's the whole idea. There's only one caveat in this model. This transition K, it has this here, this yellow-blue thingy. So place P is both having an offer and a customer. So that means that this transition K also removes a customer. Yeah, so this is also a collector of the customer. So we have a model with several initial transitions that can fire, and then a set of final transitions that can fire, the collectors. Yeah, so just looking at the net, this is what I observe. And now the property that we all would like to have is that any identifier that is being emitted should be removed by the collector. Yeah, as soon as a collector removes the identifier, then that identifier should not be there anymore. That's the basic ID. So let's check this in this model. So we create a customer. I'm not going to create any products because that's just this loop doesn't add anything. So let's fire transition G. So let's create an offer for this black customer. So that gives me a red offer. It gives me, and it gives me here in place P, it gives me a red black token because it is of the black customer of the red offer. No? So there's the coloring scheme. Okay, so transition G fired, transition H can fire. And we get a token in place here in this place before send invoice, token before deliver offer. We can deliver the offer. We can send the invoice. We may even pay the invoice. And now I arrive at a kind of a weird situation. Now this transition here, delete customer is enabled. It didn't. So if you go back, so G, this token here remains. Yes, it just puts it back. So if I now remove delete customer, I remove that token, so transition V, then there's still this token being left behind. So there's still a reference to my customer, while I said I deleted my customer. In programming code, we would call this a memory leak. And similarly, if I would remove it here, then this collector fires and the one is still here. Yeah, so what we notice is when K or V fires, moved, the identifier is not removed from the marking. So we fire a collector, the collector says, well, we reach our goal, but there are still some left. That's the part that we don't want. Yeah, so if I start looking and I want to formalize these type of properties, now we get a kind of an idea of what does it mean if I start to analyze this model. And classical Petri net properties like liveness and boundedness are not very suited because they don't take these identifiers into account. And liveness just says always every transition can fire. Boundedness says the number of tokens in each place is bound. So that means that the reachability graph is finite. Well, in this model that I just shown here, this net is unbounded because, well, there are an infinite number of identifiers being created. So boundedness doesn't really make sense. I could change boundedness slightly and just saying in any marking, the number of identifiers is bounded. Yeah, so just instead of saying, well, the whole marking should be bounded, I just say the number of identifiers that are simultaneously in my system is bounded. And in this problem, well, liveness is there in this model. Boundedness is not there, we already saw, because of the single transition. And actually, because this single transition can fire infinitely often, I also don't have width boundedness. Yeah, so at least I know that in my system there can be any number of instances at the same time. And these properties are on the system level. Yeah, so that means that we talk about the whole system. We're not talking about a single identifier and what happens. So can we find some kind of property that is on the identifier level? And one way to do this is with looking again to boundedness and then just saying, well, for any identifier in any marking, there are finitely many tokens carrying that identifier. So basically what I say is if I project on a single identifier, I project this on my reachability graph, and then that reachability graph for that identifier should be finite. Yeah, so just saying basically it says each instance needs a bounded memory. You know what the steps are, and this net is bounded. There can be infinitely many identifiers, but for each identifier, it is bounded. That's the whole idea of depth bounded. The problem is this is undecidable. And this is already undecidable if you just have one type and no type. So if all places just have a single type or no type at all, this whole setting is already unbound of undecidable. It's already known from early 2010. Too bad. So it's a nice property, but we can't do anything about it. But how about those life cycle properties I just roughly sketched in this webshop example? If I talk a bit more about this, then well, I could say something like proper type completion, because I'm interested in is each case and behaving nicely. So I could ask, what is the life cycle of this single case? Or what is the life cycle here of agents? And is that behaving nicely? And what do we then mean with behaving nicely is proper completion, for example. Saying, once a collector fired for an identifier, then that identifier is no longer in the marking, in the resulting marking. Yeah, so proper type completion just means if I fire a collector, there are no references left in the model. If I remove it, it's completely removed. Weak type termination then says, well, for any identifier, it should be possible to reach a point where we can fire the collector for that identifier. So if we have an identifier, it's always possible to remove it. That's basically the whole property. And then we say the whole net is identifier sound if this holds for all types in the net.
There may be identifiers that should not be.
Yes, but then there should be no collector. No. So if there's no collector, then this property holds because there is no collector. If there's a collector, then this property should hold. Then it can't be removed. Because that's in the definition of a collector. It removes. Yeah. And then they will be in any state because you don't remove them.
And how would you ensure soundness?
Then there's no soundness. Or because there is no collector, then proper completion is always guaranteed. And he talks something like weak termination. Is it being removed? And it's never removed. And hence, there you have the problem. It's not weakly terminating. And that's not a bad thing, because then it might be a global identifier or some global resource that you want to have different properties. But that's a different property. That's an interesting property to also look into. Are there everlasting identifiers? And what are the properties of everlasting identifiers? But that's a different property. Very interesting, actually. Yeah, so if you do it this way, and I look to this net, and here the problem was that we have this finish offer. Removing this one, then the reference in place customer would remain. Or if you fire transition V, then in place P, the reference would remain. So this net is not proper customer completing. So now I can pinpoint this model is not correct. And I can even name what the problem is. So we're already one step further. How do you analyze this? So one of the ideas that some people had was, some of my friends had was, let's take just the projection of the identifiers on the net. So what does that mean? So here we see the projection on case identifiers. So basically I just leave out everything that is not part of case. So then we see the classical net going from A, B, C, D, and with the initial and final. And then you can ask, well, is this net correct? And the answer is, of course, yes. I already showed you in one of the previous slides. And we can look at for the one where there's just the agent. So this is the net just with the agents. And well, that one is also working correctly. If you just follow everywhere where there's an agent, that works. Problem typically is if you combine them. Yeah? So I can make examples where each of the projections is correct, but the combination is not. that's the trivial ones to show. So the problem of this whole identifier soundness of each projection is not sufficient. And even worse, the property is undecidable. But as in life, when it's undecidable, it becomes fun. Because, well, I still want to say something about those systems. So in general, it might be undecidable, but can we find classes for which it works? That's the most interesting part. So what are interesting subclasses? Those are subclasses for which we can prove identifier soundness. So one of those classes is what we call extended workflow nets. So we have a workflow net, initial place, final place, some places in between. And basically what we just do is we all label them with the same type. Yeah, so let's call the type lambda. And on the arc, we have to put all the variables in order to pass it. So that's mu. So it's just everywhere the same case. We add a transition in front of it. We add a transition in the back of it, creating those identifiers. And you can prove that this one is bisimilar to the classical net. So if this net n, classical net n, is sound, then this extended net is identifier sound and live. Yeah, so this is a beautiful subclass that always works. A bit of a trivial case, of course, but at least this small case works. This shows that this whole idea that we had of coloring identifiers and then just checking for a single color, it works. That's basically what this one is saying. So we're happy. Of course, this is not really enough to start modeling. So we looked a bit further, and then we come with correctness by construction. And then we have 6 rules. So basically what it says is, if I have a single place, I can cut that place, put a transition in between. So I cut the place, I just say, well, this is the entry point where everybody produces. Then transition T fires, and then there's the next transition. And here I can just pass all the identifiers, and this still works. And so this is just passing through all identifiers. With the second rule, I cut open a transition. I just say, well, instead of having an instant transition, I have the start of the transition. Then when I'm in the phase that I executed the transition, and then I release everything and I continue. In this case, this place P should contain all information in order to pass for transition T. But it might add a new identifier, and then this transition T is the emitter, and this TC is the collector. And so I just cut it open. I make sure that all information I need is being passed, and then it still works. I can duplicate places. That's the third rule. So if I just duplicate the place and I maybe add some identifiers, or I can do anything with that place, as long as that is being transferred correctly, it still works. Same for transitions. I can just duplicate the transition, still works. I can add another transition in a self loop construct. Then it basically just says, well, I do some additional work, it still works. And the final one is, if I have a transition, I can add a resource to it. So basically, I add a resource. So this means transition T needs a resource from place P. And that resource is being created by transition TE, and it's removed by transition TC. And so basically, I just create a resource for that token, or for transition T to fire. And the resource that I create here should not be on the arrows of transition T. So it should be completely new. Yep, duplication. Yep. Exactly. So here you create a choice. So one of them will fire. Yep. Yeah. Exactly. So you create a choice. So now I have 6 rules, and any net that I create with those 6 rules will be guaranteed sound. So if I start with a single transition, that is identifier sound because it doesn't create any identifiers, and I extend the whole net using those 6 rules, then the whole net will be sound. So to give an example, we have here a net. This is the same web shop, but slightly altered so that I don't have this place with the 2 colors. And so there's no place here that remains the combination between offer and customer. And this whole net has been created using that rule. Yeah, so here there's this colored one, but it's directly being removed by this one being put. So Z is not a collector anymore because it still produces it here. No? This net is correct because I can prove it by reducing it using those rules that I just shown. So at least I can make my models very small. And for maybe I am lucky for small models that it can prove it. And for one of them, if it's a single transition that I can reduce it to, then I'm very happy because for that single transition, all properties hold. It's live, it's identified, sound, etc. So this gives me a property called correctness by construction. So for these nets, I know it's identifier sound. And then there's a third rule that I didn't put on the slide, is if I take such a place and I refine this with a generalized sound workflow net, meaning any number of tokens that I put in will be transformed to the same number of outputs. And then that net just says, well, I just pass it on. And you can show that indeed, if I refine this place with a workflow net, that is generalized sound. So for any number of tokens that you put in, the same amount of tokens will be outputted and no garbage left, then it's still correct. Yeah, so actually, this is quite a large class to model. It's not everything, because then we are undecidable. But if we limit ourselves a bit, then we can model all kinds of nice things. The only thing is, this is block structured. So you have to think in terms of what are the blocks, and if you want to go outside of a block, because not always it's possible to model something within a block structure, then you're into trouble. Then you need to do some more. So to summarize, what I've shown is two types of properties, system level and identifier level. This identifier soundness is basically this proper type completion and weak type termination. Unfortunately, it's undecidable, but for some subclasses it works. And then people always say, yeah, but why only those subclasses? And then what I always do is I end with this poem by Goethe. And if your German is not too well, that's why I did a PhD in Berlin as well. Here it's in English. It's the famous one that says, to achieve great things, we must be self-confined. Mastery is revealed in limitation. And rules alone can set us free again. So stick to the rules and you have lots of freedom to model. But you have to know what are your limitations. And that makes a master. So that is the poem of Goethe that I always say, well, this is modeling. This is what you should take into account if you start modeling. At least it's to know your classics and how to apply them and when to apply them. And that's it. So that's process and data resonance. It's the process and data resonance. It's the combination. They resonate together. They work well together.
Okay. Yes. So are there any questions from our online audience? Just raise your hand. And we did have a bunch of questions during the talk, obviously, yes. So it kind of delayed the ending of the presentation a bit. So if there are no questions, then thank you very much. So let's say one round of applause.
Thank you.
And we can move to the drinks.
That's a good part.
See you all next week. Yeah. So I can.